All right, so here we're trying to find the points on the graph of this parabola that'll be closest to the point 0, 2. So we're trying to find the minimum distance from this point to a point on this parabola. Now we're shown that the equation of the parabola is y is equal to 4 minus x squared. Now we're actually given, an equation for the distance formula to help us. So we're given a visual and some help. So let's go about this like in general, like how to start it off from like scratch per se. So make sure you always understand like what the general concept is, and don't get lost into calculus, because I've learned that sometimes students will just go and right away want to just differentiate, do some calculus, and then before they know, they get confused or make a little mistake, and then make the problem actually a lot more harder or more tedious than it needs to be. Or they just like don't know if their answer is right or wrong because they're not really even sure what their value is supposed to represent. So always keep that in mind. So what we're trying to figure out is basically what point on this parabola will give you the smallest, line segment here, which is going to be, the distance from here to here. So this point stays fixed. It could be, this distance or something like that, Again, assuming this is drawn to scale, we could probably see that this will be the minimum distance or the smallest distance to that point. So we need to find out what values of x and y will yield that minimum distance. So the idea is to find an equation for the distance and then find the minimum distance by differentiating the equation for distance and looking at the critical values. Then we can see which critical values yield a relative minimum within the domain of this problem. So let's review what the distance formula usually is written as. So we'll have d represent the distance. So the distance between 2 points x1, x1, y1, and x2, y2 will be difference between the x coordinates. So x1 minus x2 squared plus y1 minus y2 squared, all square rooted. Remember, it's just the Pythagorean theorem, solved for c. So 2 points, again, 2 points, x1, y1, x2, y2. That's what we're talking about. Okay, so then here we have the point that we're going to always have our distance come from, which is going to be 0, 2. So let's have that our x1 and y1 values will be 0 and 2. That way, that can get our formula going somewhat. So let's have let's rewrite the distance as, actually let's make this x2 and y2 because I think the math will be just a little easier to work with. Again, it does not matter if you want to make that x1, y1. I'm just doing it because usually the math looks a little cleaner. So we're going to have x1 minus 0 squared plus y1 minus 2 squared in our distance equation. Now, we can't straight up differentiate the distance equation yet because we have two variables in here. So we have x and y. So we need to write this distance equation in terms of just one variable. And let's just rewrite it in terms of x, because we're used to working with functions of x. So we're gonna need to find an equation for y in terms of x. Now, we're given that the parabola's equation is is equal to y is equal to 4 minus x squared because the parabola is a function of x. So any y value on this parabola can be given by this equation. So then what we can do is instead of having that y value there, we'll just make that 4 minus x squared. And so then that'll give us that the distance equation will be the square root of x1 minus 0 squared plus 4 minus x squared minus 2 all squared within there. So let's simplify this formula, or clean it up, you know, so it's easier to work with. So x1 minus 0 is just x1 squared plus, so we're gonna have 4 minus 2, that just becomes 2 in there. So it becomes 2 minus x squared squared. So in here we just have, let me write it up here, 2 minus x squared all squared. And that's what that'll become. So just following out or multiplying out mentally, 4 minus 2x squared minus 2x squared, so minus 4x squared plus x to the 4th. Now, that's x1 notation. It doesn't really matter that we call it x1 because in general, it's just, remember, it's a subscript. So we can just, you know, have these all be x1 or just call them in general x. It doesn't really matter. So let's rewrite this as the square root of what we have is negative 3x squared plus 4 plus x to the 4th. And let's go in standard form. So x to the 4th minus 3x squared plus 4. So here we got our primary equation. Primary equation. Using the color because it's a big deal. The primary equation, you know, is usually the key in solving these problems. And it's not always so easy to do because you really got to be creative sometimes, especially if you're not used to working with like physics types problems. But the good thing is once you get to this, it's really just applying the calculus techniques. So we basically just need to find the relative minimum for this equation or this function, we can say. So let's write this, you know, as it's already, you know, an equation in terms of x. Now let's recognize that if we're taking the square root of a number, this this equation will have its minimum when the expression on the inside is minimized. So to make our life simpler, we can just make our function equal to x to the 4th minus 3x squared plus 4. That way we don't have to worry about differentiating the square root. Because again, as long as this is minimized, the whole function will be minimized. So you don't have to worry about that. So we're going to make our function, we'll name it f of x is equal to x to the 4th minus 3x squared plus 4. So let's differentiate this and find the critical values. So we're going to have f prime of x be 4x cubed minus 6x. Find critical values. So find where this is equal to 0 or where it's undefined. So 0 is equal to 4x cubed minus 6x. From algebra, 6x equals 4x cubed. We'll now way through, divided by x, divided by 4. So we'll get 6/4 equals x squared, or 3/2 equals x squared. So then the square root of 3/2 will be x. So then x will be, our critical values would be the positive square root of 3/2 and the negative, you know, negative square root of 3/2. We got our two critical values here. This function is defined for all x values, so we don't have to worry about any undefined values. So we have two critical values. Now, unlike the problems before this one, since we're talking about points on a plane, it's okay for x to be a negative number, because a negative number would be just on this side of the parabola. So both of these are valid. Both of these are valid to be potential, x values that will yield the smallest distance. So let's see what's going on at these values, and to do that, I would probably just let's use the first derivative test. Let's see what's going on before, between, and after. So I'm gonna make up my table where I have an interval in the top row. So negative infinity to negative root 3 over 2. And negative root 3 over 2. Oh, well, I almost forgot. Whoa. Another critical value. Another critical value would just be 0, because this will be, have a solution. Let's make that x3. x3 would be 0. Whew. That would have been that would have kind of made our work a little more confusing. But okay, 3 critical values: 0, negative root 3 over 2, positive root 3 over 2. So we're gonna go from negative root 3 over 2 to 0, and then from 0 to positive root 3 over 2, and then from root 3 over 2 to infinity. And let's pick a test value. Pick numbers that are easy to work with. So I would pick, maybe x is negative 2 in this interval, x is 0.5, or x is negative 0.5 here, and then positive 0.5 here. And then x equals 2 here. And then we want to see what's going on with the first derivative. Like, is the sign of the first derivative positive or negative in each interval? So we really just need to figure out the sign of the first derivative, because that's going to tell us if the function is increasing or decreasing. So let's set up another row here. So I'm gonna do essentially like the graph of f of x. Again, I like visuals. Okay, so f prime of negative 2. We're gonna plug that into here. F prime of negative 2, and you'll get 4 times negative 2 cubed, negative 8, minus 6 times the negative 2, negative 32 plus 12, so it'll be negative 20. You get a negative number here, negative. So go ahead, I'm gonna time travel right now, so you can go ahead and pause the video and then evaluate this. You can check your answers. Once you're ready to check your answers, unpause it. Okay, so you should get a positive value for the derivative when x is negative 0.5, a negative when x is 0.5, and a positive when x equals 2. Now, remember, when the derivative is negative, this tells you that the graph of the function is decreasing. I cannot fit that there. Decreasing, you get the idea. Decreasing, it's going down. When it's positive, it's increasing, it's going up. So it's going up here, and down here, down here. So over here, as it's going down, then up, here we have a relative minimum. I'm gonna switch my pen. I don't like how this pen is drawing right now. Relative minimum here. Over here, since it's increasing then decreasing, here you have a relative max. And then here, decreasing and increasing. So over here, you have a relative minimum again. Relative minimum. So relative max, relative minimum, and two relative minimums. So essentially, we're gonna have our minimum distances occurring at negative √3/2 and positive √3/2. Now you could probably guess that these values will be equivalent since we have, a parabola and we can easily see. But let's just go ahead and plug it in and see exactly what values we'll get for the distance just to reinforce that we're doing this correctly. So let's first write relative minimums. Since this occur at x equals negative √3/2 and x equals positive √3/2. Oops. So let's just basically plug these in to our distance equation. This are the one that's simplest, this one right here. And let's see what we get. So we're going to plug these into here. So our distance will be square root of, if you plug in there, and you raise in either of these to the fourth, you'll get √3/2 times √3/2, so you get 9/4 minus 3 times 3/2 plus 4. And when you go ahead and you work this out, you'll get the distance is equal to the square root of 1.75, which will be about 1.32 or 1.32 units. If you want to go further in the problem and figure out the actual answer. All right, and there you go.